quantum mechanical model of an atom. First, you must know, before we studied the classical mechanics. What is that classical mechanics? Based on the Newton's law of the motion. That describes the motion of all macroscopic, that means the larger one, the macroscopic objects such as falling in a stone, orbiting planets, etc., which have the essentially a particle-like behavior. That already we were seeing. However, it is fails when applied in the microscopic. This is for applicable in macroscopic. In microscopic objects like electrons, atoms, molecules like this. So this is mainly because of the fact of the classical mechanics ignores the concept of the dual behavior of the matter, especially the subatomic particles, and the uncertainty principle. So the branch of the science that takes into account this dual behavior of matter is called quantum mechanics. The quantum mechanics is a theoretical science that deals with the study of the motion of the microscopic objects. So that have the both observable wave-like and the particle-like properties. So it specifies the law of motion that these objects obey. So when the quantum mechanics is applied to macroscopic objects, the result are the same as the from the classical mechanics. The development of the quantum mechanics, there is independently Werner Heisenberg and Erwin Schrödinger. That is the famous equation, Schrödinger wave equation. However, we shall discussing the quantum mechanics, which is based on the ideas of wave motion, the fundamental equation of the quantum mechanics. Like first, for a system, the molecule whose energy does not change with the Schrödinger equation is simply we can write H cap psi is equal to E psi. Here the H cap is a Hamiltonian operator, that is Hamiltonian operators. Then the psi is a wave function. Hamiltonian operator, psi is a wave function. Here this H psi is equal to E psi. The Schrödinger gave a, see this operator, this is the Hamiltonian operator. This operator forms a form the expression for the total energy of the system. That is, the total energy of the system take into account the kinetic energy of all subatomic particles, that is electrons, nuclei, like that. The attractive potential between the electrons and the nuclei and repulsive potential among the electrons and the nuclei individually. This solution, that is E and psi, energy and the psi wave function. Here the hydrogen atom and the Schrödinger equation. Schrödinger equation. The Schrödinger equation solved for the hydrogen atom, the solution gives the possible energy levels electron can occupy the corresponding wave function, that is psi of the electron associated with the each energy level. So the quantized energy state and the corresponding wave function, which are characterized by the 3 quantum numbers. That is, namely, principal quantum number, asymptotal quantum number, and the magnetic quantum number. The quantum number arises the natural consequence in the solutions of this Schrödinger equation. When an electron is in energy, in any energy state, the wave function corresponding to that the energy state containing all information about the electron. So the wave function, the mathematical function whose value depends upon the coordinates of the electron in the atom and does not carry any physical meaning. See, such wave functions of the hydrogen or the hydrogen-like species with one electrons are called atomic orbitals. Here the such wave function that pertaining to the one electron species are called one electron system. The probability of the finding electron at a point within an atom the proportional to the modulus of psi square. At that point, that quantum mechanical result that hydrogen atoms successfully predict that all aspects of the hydrogen atom spectrum, including some phenomena that could not be explained in the Bohr model. That application of Schrödinger equation to multi-electron atoms presents a difficulty. That Schrödinger equation cannot be solved exactly for a multi-electron atom. One electron atom is possible, but multi-electron is some difficulties are there. This difficulty can be overcome by using the bond approximation method, or you can tell approximate methods. There's such calculation with the aid of modern computers so that the orbitals in the atom other than the hydrogen do not differ if in any radical way from the hydrogen orbital. Already we discussed. That is the principal difference lies in the consequence of the increased nuclear charge. Because of this, all orbitals are somewhat contracted. So that further, that's mean you will study later. That's mean you will learn later. That's mean quantum numbers, shape of the orbitals we will discuss later. Unlike the orbitals of hydrogen or the hydrogen-like species, whose energy depends only on the quantum number, that is the quantum number n. The energy of the orbitals in multi-electron atom depends on the quantum number of n and l. Small n. Here the important features of the quantum mechanical model of atom. The quantum mechanical model of an atom, the picture of the structure of the atom, which emerges from the application of the Schrödinger equation to atom. The first one, the energy of electron in atoms in quantized. For example, the electrons are bound to the nucleus into atom. So electrons are bound to the nucleus in atom. Then the existence of quantized electronic energy level is a direct result of the wave-like properties of electron and are allowed solution for the Schrödinger wave equation. Then both the exact position and the exact velocity of an electron in an atom cannot be determined simultaneously. That is in Heisenberg uncertainty principle. The path of an electron in an atom therefore that can never be determined or known accurately. So that is why that's why we will see later, that is only the probability of finding the electron at a different point in an atom. That's the fourth one. Is the atomic orbital is the wave function, that is psi. Wave function is psi. For an electron in an atom, whenever an electron is described by a wave function, we say that the electron occupies that orbitals. Since many such wave functions are possible for an electron, there are many atomic orbitals in an atom. These one electron orbital wave functions are orbital forms the basis of the electronic structure of atom. So in each orbital, the electron has a definite energy. An orbital cannot contain more than 2 electrons. In a multi-electron atom, the electrons are filled in various orbitals in the order of the increasing energy. For each electron of a multi-electron atom, there shall be orbital wave function, the characteristics of the orbital it occupies. That means all the information about the electrons in an atom is stored in the orbital's wave function, and the quantum mechanics makes it possible to extract the information about the wave function, that is out of wave function. The probability of finding of electron at a point within an atom is proportional to the square of the orbital wave function, that is psi square. At that point, the psi square known as the probability density and is always positive. Here this always from the value of psi square at the different points within an atom, it is possible to predict the region around the nucleus where the electron will most probably be found. Then orbitals quantum numbers. A large number of orbitals are possible in an atom. Qualitatively, these orbitals can be distinguished by their size, shape, and the orientation. So an orbital of smaller size means there is more chance of finding of the electron near the nucleus. Similarly, shape and the orientation mean that there is no more probability of finding of the electron along the certain direction than along this. Atomic orbitals are precisely distinguished by what are known the quantum numbers. That's each orbital is designed by 3 quantum numbers. They are labeled as N, L and ML. Here the N, that is the principal quantum number. First one is principal quantum numbers. Then second one is asymptotal quantum numbers. Then third one is magnetic quantum number. First, the principal quantum number. This is N and this is L and this is ML. Here the N is a positive integer with the value as N is equal to 1, 2, 3, 4 and so on, like this. The principal quantum numbers determine the size and the large extent the energy of the orbital. For hydrogen atom and hydrogen-like species, for example, He 2 plus, lithium 2 plus, helium 2 plus, like this extra. The energy of the size of the orbitals depends only on the N. So the principal quantum number also identify the cell. With the increase in the value of N, that is 2, 3, 4 like this, the number of allowed orbital increases and are given by N square. The all orbitals are given the value of N constitute a single cell of atom and represented by N is equal to 1, 2, 3, 4 like this, means the cell will be K, L, M, N like this. So size of orbital increase with the increase of principal quantum number. In other words, the electron will be located away from the nucleus. Since the energy is required in the shifting away the negatively charged electron from the positively charged nucleus. So the energy of the orbital will increase with the increase of N value. So the next is asymptotal quantum number. The asymptotal quantum number, that is L. It is also known as the orbital angular momentum or the subsidiary quantum number. It defines the three-dimensional 3D space, that is three-dimensional shape of the orbital for a given value of N and L. Can have N values are ranging from 0 to N minus 1. That is, for the given value of N, the possible value of L are, that means L is equal to 0, 1, 2 like this up to N minus 1. For example, when N is equal to 1, value of L is equal to what? 0 only, because only 1 values are there. For N is equal to 2, the possible value is L is equal to, L value can be 0 and 1 because N is equal to 2, so that 0 and 1. Suppose N is equal to 3, the L value will be 0, 1, 2. So like this. So each cell consists of one or more subshell or sublevel. This number of subcell in a principal cell is equal to the value of the N. For example, the first cell N is equal to 1, there is only one subcell because of L is equal to 0. There are suppose 2 subcell, that is L is equal to, N is equal to subcells means L is equal to 0, 1. In second cell N is equal to 2, 3, that means 0, 1, 2. So in third cell N is equal to 3. So like this, each subcell, suppose N is equal to 4 means L is equal to 0, 1, 2, 3. So the subcell, each subcell assigned an asymptotal quantum number that is called L. The subcell corresponding to the different value of L, that's values of L. Here 0, 1, 2, 3, 4, 5 and so on. Here the notation for subcell will be S, 0 for S, 1 for P, 2 for D, 3 for F, 4 for G, 5 for H, like this and so on. Then the principal that's mean the values of the L for given principal quantum numbers are the corresponding subshell to the notation. For subshell notation, I will show you, that is N, L and subshell notation or notation for subshell. Here n is equal to 1 means L is equal to 0. The subshell notation is 1s. 2, L is equal to 0. The subshell notation is 2s. Then n is equal to 2, L is equal to 1. Another possibility, that means 2p. Then n is equal to 3, L is equal to 0, means the subshell will be 3s. N is equal to 3, L is equal to 1, that will be 3p. N is equal to 3, L is equal to 2, that subshell will be 3d. Then for n is equal to 4, L is equal to 0, 4s. N is equal to 4, L is equal to 1, 4p. N is equal to 4, L is equal to 4d. Then n is equal to 4, L is equal to 3, this means 4f. So this is the subshell's notation. The magnetic orbital quantum number. This information about the gives the information about the spatial orientation of the orbital with respect to the standard set of the coordinate axis. For any subshell that is defined by the L value. Here 2L plus 1 values of ML, that is values of ML, that is possible, and these values are given like this: ML is equal to minus L to minus L minus of L minus 1 minus of L minus 2, like this. Then 0, 1, then positive value. Here the negative value, then it will become 0, then positive value will start. 1, L minus 2, or you can write like this: L minus 2, L minus 1 and L. Look at here, the negative value and the L value, L and the positive L. So this for suppose L is equal to 0, the value, they only permitted the value of ML is equal to 0. That means you can apply this formula, and this L value is what? 0. So that 0, 2 into 0 plus 1, it will become what? 1. That is 1s orbital. For L is equal to 1. And so that means L is equal to 1 means ML should be what? Minus 1, 0 and plus 1. Because the value minus 2 plus, so that minus 1, 0, then started was plus 1. So here L is equal to 1. Apply this formula 2L. So L is equal to 1, 2 into 1 plus 1, 3. That means this is 3p orbital. This is 1s orbital and this is 3p orbital. When L is equal to 2, the ML will be what? Minus 2, minus 1, 0, plus 1, plus 2. So here this means 2 into 2 plus 1, it will become 5. So this is 5d orbitals. So it should be noted that the values of ML are derived from the L and that values of L are derived from N. So each orbital in an atom therefore is defined by a set of values for N, L and the M. N, L and ML. An orbital described by the quantum numbers, that is N is equal to 2, L is equal to 1, is N is equal to 2, L is equal to 1, ML is equal to 0, is an orbital in the p subshell of the second cell. See? look at this. This table gives the relation between the subshell and the number of orbital associated with it. So value of L 0 1 2 3 4 5, subshell notation S P D F G H. The number of orbitals like this 1 3 5 7 9 11. Then the electron spin. The electron spin, 3 quantum numbers are labeling the atomic orbital, and that is used equally well to the definite energy, that is shape and orientation. But all these quantum numbers are not enough to explain the line spectra observed in the case of the multi-electrons atom. That is, some of the lines actually occur in doublet, that is 2 lines. Doublets mean 2 lines. Simply you can write doublets. Triplets, 3 lines. 3 lines closely spaced. This suggests the presence of the few more energy levels than predicted 3 quantum numbers, that is electron spin. Simply yes. So here the 4th quantum number, that is known as the electron spin quantum number, or ms. The electron spin quantum numbers spins around its own axis, much in similar way as Earth spin around the own axis while they revolving around the sun. So in other words, an electron has besides charge and mass intrinsic spin angular quantum number. Spin angular quantum momentum of electron, a vector quantity, so can have 2 orientation relatively to the chosen axis. These 2 orientations are distinguished by the spin quantum number, which is, that is ms is equal to plus half and r minus half. These are called 2 spin states, that is 2 spin state of electron. Normally they are represented in arrow. Plus arrow indicates, plus half indicates up arrow, and the minus half indicates down arrow. So the 2 electrons have different ms value, that is ms spin value. That is, one is plus half, another one is minus half, are said to have the opposite spin. The orbital cannot hold more than 2 electrons. This is very important. The orbital cannot hold more than 2 electrons, and these 2 electrons should have the opposite spin. This means like this. This is the possible, not more than. Suppose an orbital, suppose subshell having 1 r maximum opposite spin like this. This is the possible. Then the sum of the quantum numbers, that is n, that is the conclusion of that quantum numbers. N definites the cell, determine the size of the orbital, and also the large extent energy of the orbital. There are n subshells in the nth cell. L indefinites the subshell and determines the shape of the orbitals. That we will see in shape of atomic orbital later in the next session. There are 2l plus 1 orbitals, each type in a subshell. That is 1s orbital, not 1s orbital. 1s orbital L is equal to 0, 3p orbital L is equal to 1, and 5d orbital L is equal to 2. Already we were saying, that is per subshell. To some extent, L also determines the energy of the orbital in the multi-electron atom. Then ml designates the orientation of the orbital for a given value. ml has 2l plus 1 value, the same as the number of the orbital per subshell. It means that the number of orbital is equal to the number of ways in the which they are oriented. That ms spin quantum refers to orientation of the spin of the electron. Then we will discuss the shape of atomic orbital.